This is the story of why the universe, which by every calculation should be overflowing with advanced civilizations, appears to be completely empty, and what that silence might mean for us. There is a theory, one that has been quietly haunting astronomers, physicists, and philosophers for decades, that suggests most intelligent life in the cosmos rises, struggles, reaches for the stars, and then vanishes forever, leaving behind nothing but silence and dead worlds. The universe, in other words, may not be a cradle of life. It may be a graveyard. Before we dive in, if mind-bending cosmic rabbit holes are your thing, hit the like and subscribe button. It takes 2 seconds, but it's what keeps this channel alive and the content coming. Now settle in, because things are about to get interesting. Picture the night sky. Not the washed-out, light-polluted version most of us see from cities, but the full thing. The sky that ancient farmers and sailors looked up at, that billions of stars burning across the dark above us. For most of human history, staring into that immensity produced feelings of wonder, of smallness, of mystery. But sometime in the 20th century, a new feeling crept in, something quieter and harder to name. Because when scientists began seriously calculating how many stars are up there, how many planets orbit those stars, and how many of those planets could in principle support life, they kept arriving at the same uncomfortable conclusion. The universe should be absolutely teeming with intelligent life. And yet when we look up, when we listen, when we point our most sophisticated instruments at the sky, we find nothing. Not a signal, not a structure, not a single whisper from another mind anywhere in the cosmos. That silence is the Fermi Paradox, and it is one of the deepest, most unsettling puzzles in all of science. The man at the center of it was Enrico Fermi, an Italian-American physicist and Nobel laureate who, during a lunch conversation in 1950, asked his colleagues a deceptively simple question: where is everybody? Fermi had been thinking about the vastness of the universe and the astronomical number of opportunities for life to have evolved somewhere out there. And the obvious counterweight to all of that, the complete absence of any evidence that it had. His question was casual, almost throwaway, the kind of thing you say between bites of food, but it lodged itself in the scientific imagination and has never quite let go. To understand why that question is so strange and so profound, you have to grapple with the numbers. The Milky Way galaxy alone contains somewhere between 200 and 400 billion stars. Around those stars, based on data gathered over decades of exoplanet research, there appear to be billions of planets. On November 4, 2013, astronomers using data from NASA's Kepler space mission reported that there could be as many as 40 billion Earth-sized planets orbiting in what scientists call the habitable zone, the distance from a star where liquid water can exist on a planet's surface, within the Milky Way alone. About 11 billion of those planets are estimated to be orbiting sun-like stars, and our galaxy is just one galaxy. There are roughly 2 trillion galaxies in the known universe. When you start stacking those numbers, the conclusion seems inescapable. Life must have evolved somewhere else. Almost certainly many, many times. And yet, silence. The universe has been around for 13.8 billion years. Our own solar system only formed about 4.6 billion years ago. That means there were entire star systems forming, maturing, and potentially producing intelligent life billions of years before Earth even existed. If even one of those civilizations had survived and decided to expand through the galaxy at even 1% of the speed of light, which is far slower than many theoretical propulsion concepts suggest, they could have colonized the entire Milky Way many times over by now. British physicist Michael Hart framed this mathematically, pointing out that at 1% of light speed, a galaxy 100,000 light-years across would be fully colonized in about 10 million years. A cosmic eye blink in the 13.8 billion-year lifetime of the universe. We should be surrounded by evidence of ancient galactic civilizations. We are not. This is the core of Fermi's paradox. Not just that we haven't found anyone, but that a universe old enough and large enough to have spawned thousands or millions of civilizations seems to have produced exactly one that we know about. Us. And us only here on this one small rocky planet, orbiting a fairly ordinary star in an unremarkable region of a medium-sized spiral galaxy. In 1961, 11 years after Fermi's question, astronomer Frank Drake sat down to organize the agenda for a conference at the National Radio Astronomy Observatory in Green Bank, West Virginia. The conference was about the search for extraterrestrial intelligence, and Drake wanted a framework for thinking about the problem. What he came up with, almost as a bookkeeping tool for the meeting's agenda, ended up becoming one of the most famous and debated equations in scientific history. The Drake equation is a multiplication of several factors, each representing a step in the chain of events that leads from a star being born to an intelligent civilization transmitting radio signals across the galaxy. The factors include things like the rate of star formation in the galaxy, the fraction of those stars with planets, the number of planets per star system that could support life, the fraction of those planets where life actually develops, the fraction of those life-bearing planets where intelligence eventually emerges, the fraction of those intelligent species that develop technology detectable from space, and finally, perhaps most critically, the average length of time such a civilization continues to transmit those signals. Multiply all of these together, and you get n, the estimated number of communicating civilizations currently operating somewhere in the Milky Way. Drake first unveiled this equation at that Green Bank conference in 1961, a meeting that brought together a small, eclectic group of experts, including a 27-year-old Carl Sagan, who would go on to become arguably the most famous science communicator in history. John Lilly, who studied dolphin language and communication, was also there, so the group rather whimsically called themselves the Order of the Dolphin. The problem with the Drake equation is both its genius and its limitation. It forces you to think carefully about each step in the chain, but most of the numbers are deeply uncertain. We know some things with reasonable confidence. We know how many stars form each year in the Milky Way. We have decent data on the fraction of stars with planets. But the further you go down the chain, especially into the biology, the emergence of intelligence, the development of technology, and the crucial question of how long a civilization lasts, the numbers become essentially guesses. Frank Drake himself, working with certain optimistic assumptions, suggested that n might be around 10,000. Carl Sagan, in 1974, estimated there might be as many as 1 million advanced civilizations in the Milky Way alone. Other estimates have ranged from 1, meaning we are alone, to several million. The range is staggeringly wide, and it is wide precisely because we don't know. That uncertainty is not a flaw in the equation, it's the point of it. The equation is a map of our ignorance, a structured way of identifying what we need to learn if we want to know whether we are alone. But here is the thing that makes all of this so deeply uncomfortable. If even the moderate estimates are anywhere close to right, there should be abundant evidence of other civilizations all around us. The fact that there isn't any, that's the paradox. That's the mystery that has never been solved. Into that mystery, in August 1996, an economist named Robin Hanson introduced an idea that has been haunting scientists ever since. Hanson published an essay titled "The Great Filter: Are We Almost Past It?" And in it, he proposed a deceptively simple solution to the Fermi Paradox. The argument goes like this: somewhere between the formation of a habitable planet and the rise of a civilization capable of colonizing galaxies, there must be a step, or maybe more than one step, so difficult, so unlikely, that almost nothing makes it through. This is the Great Filter, a bottleneck so severe that out of all the billions of worlds that might have started down the path toward intelligent life, only a tiny handful, maybe just one, actually makes it to the other side. Hanson's 9-step model traces the path from dead matter to a spacefaring civilization. Step 1 is finding the right star system, one with the necessary chemistry and the right kind of planets. Step 2 is the emergence of reproductive molecules, the very first stirrings of something like life. Step 3 is the development of single-celled life. Step 4 is the jump from simple prokaryotic cells to complex eukaryotic cells, the kind that have a nucleus and internal structure, the kind that eventually lead to complex organisms. Step 5 is multicellular life. Step 6 is sexual reproduction and the diversity it produces. Step 7 is the emergence of tool-using, language-capable, intelligent beings. Step 8 is the technology to reach the stars. And Step 9, the final destination, is that civilization actually doing it, actually expanding beyond its home system and colonizing the observable universe. According to the Great Filter hypothesis, at least one of these steps must be extraordinarily difficult. Something in that chain of events is so unlikely that almost no world ever completes it. And the crucial, terrifying question that Hansen put at the center of his essay, the question that keeps researchers up at night, is this: where in that chain does the filter lie? Is it behind us, or is it still ahead? If the great filter is behind us, if one of the early steps in that chain is vanishingly rare, then we are survivors. We are one of the handful of lineages that got through the bottleneck by sheer luck or some unusual combination of circumstances. That's actually reasonably good news. It means the road ahead might be open. It means the hard part is done. It means we might really have a future among the stars. But if the great filter is ahead of us, if civilizations routinely get to roughly where we are now, and then something happens, then we are in serious trouble. It means we are not survivors. We are the next in line. And the silence of the universe around us is not emptiness. It's a graveyard. The first possibility, that the filter is behind us, sends you diving into the deep history of life on Earth and asking which of those steps was genuinely improbable. And there are a few very compelling candidates. The first, and perhaps most profound, is what scientists call abiogenesis, the origin of life itself, the moment when chemistry becomes biology, when a collection of molecules arranged in just the right way starts doing something that no mere chemistry does, replicates itself, metabolizes, responds to its environment. That transition, from non-living to living, from the complexity of organic chemistry to the self-sustaining complexity of a living cell, has only happened once that we know of on Earth, and we genuinely do not know how it happened. We can build reasonable hypotheses. The RNA world hypothesis suggests that self-replicating RNA molecules may have been the first step, since RNA can both store information like DNA and catalyze reactions like proteins. But we cannot replicate it in a laboratory, cannot say with confidence how likely it is, and cannot be sure whether it's something that happens easily given the right conditions, or something that requires a near-miraculous combination of circumstances. A 2025 study by Robert G. Endres used information theory to argue that the spontaneous emergence of life from protocells is highly improbable under random conditions on early Earth, quantifying informational barriers and reinforcing abiogenesis as a potential primary filter. If that's right, if the origin of life is astronomically unlikely, then almost every rocky planet in the habitable zone of its star sits barren, waiting forever for chemistry to become biology, and almost none of them ever makes it. The universe is not full of dead civilizations. The universe is full of beautiful empty worlds, and Earth got astronomically lucky. The second candidate is the transition from simple, single-celled prokaryotic life to complex eukaryotic life. Life on Earth has existed for at least 3.8 billion years. For roughly the first 2 billion of those years, more than half of life's entire history on our planet, the only life that existed was simple single-celled organisms, bacteria and archaea. These life forms are extraordinarily resilient, extraordinarily diverse, and extraordinarily successful. They have colonized essentially every environment on Earth, from deep-sea hydrothermal vents to glaciers to strongly acidic hot springs. But they are simple. They don't have a nucleus. They don't have complex internal organelles. They reproduce by dividing. They are, in the deepest sense, very basic. The transition to eukaryotic cells, cells with a true nucleus, with mitochondria, with the internal complexity that makes animal and plant life possible, appears to have happened just once in the history of life on Earth. One cell, roughly 1.5 to 2 billion years ago, was engulfed by another cell, and instead of being destroyed, it was incorporated, and over evolutionary time, it became the mitochondria, the power plant of every animal cell on the planet. This event, called endosymbiosis, allowed for a dramatic increase in the energy available to a single cell, which eventually made multicellular complexity possible. But it only happened once. That could mean it's so unlikely that it almost never happens anywhere in the universe. And if intelligence requires eukaryotic complexity, and eukaryotic complexity is a near miracle, then once again, we are survivors. Then there is the jump from single-celled life to complex multicellular life, which happened about 600 million years ago and led to the Cambrian explosion, that remarkable burst of biological innovation when nearly every major animal body plan currently on Earth appeared in the fossil record within a relatively short window of geological time. Paleontologist Peter Ward and astronomer Donald Brownlee argued in their book Rare Earth, published in 2000, that this transition, like so many others, required such a specific and unlikely combination of planetary, geological, and evolutionary circumstances that it is probably extraordinarily rare in the universe. Their book laid out the case for what they called the rare Earth hypothesis, the idea that while simple microbial life might be common, the conditions needed for complex animal life are so specific that Earth is probably one of very few places in the universe where it has arisen. Ward and Brownlee's list of required conditions is long and humbling. It includes being in the right part of the galaxy, not too close to the dense, radiation-heavy galactic center, not so far out in the sparse galactic rim that the right heavy elements aren't available. It includes having the right kind of star, stable enough, not too hot, not too cold, with a long enough lifespan to allow billions of years for life to evolve. It includes having a planet in the narrow habitable zone where liquid water can persist on the surface for billions of years. Having plate tectonics to recycle carbon and regulate the climate over geological time. Having a large moon, our moon is unusually large relative to Earth, to stabilize the planet's axial tilt, which keeps the climate stable enough for complex life to persist. Having a large outer planet like Jupiter to act as a gravitational shield, deflecting the most dangerous asteroids and comets that would otherwise bombard the inner solar system. Having a planetary magnetic field to deflect the solar wind and preserve the atmosphere. Every one of these factors that Ward and Brownlee describe is a requirement that must be met simultaneously. And the more factors you add to the list, the lower the probability becomes that any given planet in the universe meets all of them. Their conclusion was stark. Earth is probably rare. Complex life like ours is probably rare, and intelligent life, which requires complex life as its foundation, is probably extremely rare. The silence of the universe might not mean something killed everyone. It might mean almost no one ever got started. But here is where the story gets genuinely chilling, because there is another possibility, the other answer to where the filter lies, and it is much, much darker. What if most of the steps to intelligence are not actually that hard? What if abiogenesis happens readily? What if the jump to eukaryotic complexity happens again and again across the universe? What if complex multicellular animals are a normal product of evolution on rocky planets with the right chemistry? What if intelligence itself, tool use, language, the ability to build technology, is something that evolution tends to produce given enough time, because intelligence is adaptive enough that natural selection rewards it wherever it arises? If all of that is true, then the universe should be full of civilizations that have reached roughly where we are now, and the fact that we see no evidence of any of them means something happened to all of them, something that comes later, something that is waiting for us. This is the version of the Great Filter that Nick Bostrom, a philosopher at Oxford University, wrote about in his 2008 essay titled, "Where Are They? Why I Hope the Search for Extraterrestrial Intelligence Finds Nothing." The title alone tells you something about the emotional weight of the argument. Bostrom pointed out that discovering evidence of life elsewhere, especially complex multicellular life, especially intelligent life, would be, in a sense, terrible news for humanity, because it would tell us that the filter is not behind us. It would tell us that intelligence arises routinely, that civilizations form routinely, and that all of them, without exception, hit a wall. And if all of them hit the wall, then we are about to hit the wall too. Think about what that wall might be. There are several candidates, and none of them make for comfortable reading. The most obvious one, especially to anyone who lived through the Cold War, is nuclear weapons. Humanity discovered the fission of uranium in the 1930s, built the first nuclear bomb in 1945, and has spent every year since then living under the shadow of the possibility that someone, someday, will use them in sufficient numbers to trigger what scientists have called nuclear winter, a scenario in which the soot and particulate matter thrown into the atmosphere by burning cities blocks sunlight, causing temperatures to drop, agricultural systems to collapse, and civilization to unravel. Studies have confirmed that even a limited exchange of nuclear weapons, not a full-scale war, just a regional conflict, could have devastating effects on global food production and climate. Russia and the United States are estimated to have around 5,580 and 5,225 nuclear weapons respectively, as of early 2025. The total global stockpile runs into the thousands of warheads, each carrying more destructive power than all of the bombs dropped in all of World War II combined. Now imagine a civilization roughly as technologically advanced as ours, maybe a few centuries ahead of us. They discovered nuclear energy, because nuclear energy is a natural consequence of understanding atomic physics, and atomic physics is something that any civilization studying matter deeply enough will eventually arrive at. They built weapons, because that is what civilizations under competitive pressure have historically done with every new energy source. And then, what? Did they use them? Or did they find a way through? The silence of the universe offers no reassurance on this point. The second candidate is climate change, the transformation of a planet's atmosphere through industrial activity to the point where the conditions that supported complex life no longer exist. Here on Earth, the burning of fossil fuels over the past 2 centuries has increased atmospheric carbon dioxide concentrations to levels not seen for millions of years, raising global temperatures, disrupting weather patterns, threatening food and water supplies, and creating feedback loops that may become self-reinforcing and difficult to reverse. A civilization that develops industrial technology but does not transition away from its planet-altering energy sources in time might find that it has slowly made its homeworld uninhabitable, not through any single catastrophic event, but through a slow, grinding series of consequences that compound and escalate until the systems that supported civilization can no longer sustain it. And perhaps most troubling of all, because it is the most recent and least understood, artificial intelligence. In 2024, astronomer Michael Garrett, the Sir Bernard Lovell Chair of Astrophysics at the University of Manchester and director of the Jodrell Bank Centre for Astrophysics, published a paper in the journal Acta Astronautica arguing that artificial intelligence could represent the critical filter for technological civilizations. Garrett's argument is that even before artificial intelligence becomes superintelligent, even before it becomes autonomous, it is likely to be weaponized by competing groups within civilizations seeking advantage over each other, and that the trajectory from widespread AI adoption to some kind of catastrophic destabilization might be shorter than the trajectory from AI adoption to becoming a truly multiplanetary species, which would be the key survival insurance against any single planet catastrophe. Garrett estimated that the communicative lifespan of civilizations once they adopt AI in widespread use might be around 100 to 200 years, a very narrow window. In the context of cosmic time, 100 years is nothing. And if AI civilizations are appearing and disappearing within a couple of centuries of developing the technology, the chances that any two of them overlap in time and space closely enough to detect each other become vanishingly small. The galaxy might be full of the ashes of AI civilizations that burned bright and vanished before they ever made contact with anyone. Let's step back for a moment and think about the Fermi Paradox from a different angle, because there are quite a few different hypotheses people have proposed for why the universe seems so empty, and not all of them require that something catastrophically bad happens to every civilization. One of the oldest alternative explanations is something called the zoo hypothesis, first proposed by scientist John Ball in 1973. The zoo hypothesis suggests that advanced civilizations know we are here. They have detected us, perhaps long ago, and have made a deliberate choice not to contact us. Maybe we are too primitive to be worth talking to. Maybe there is a cosmic equivalent of a nature reserve or a protected wilderness, and Earth sits inside it. Maybe there is some kind of galactic club or federation that waits until a civilization reaches a certain level of maturity or sophistication before extending an invitation to make contact. It's a flattering idea in some ways, the notion that we are being watched and protected and will eventually be welcomed into a broader community of minds. It's also deeply unfalsifiable, which makes it scientifically frustrating. You can't prove you're not in a zoo. You can't prove that the silence around you isn't a deliberate, carefully maintained policy, rather than simply the actual absence of anyone to make noise. Then there is what astronomers sometimes call the rare Earth variation, which we've touched on already. The idea that intelligent life is so rare that there simply aren't many civilizations in the observable universe, and the ones that exist are so far apart that communication is essentially impossible given the speed of light. The nearest star to our own Sun is Proxima Centauri, about 4.2 light-years away. Even traveling at the speed of light, which nothing with mass can actually do, a radio signal to Proxima Centauri takes 4.2 years to arrive, and the response takes 4.2 years to come back. A conversation would take nearly a decade per exchange. Over larger distances, the communication times become geological. And if intelligent civilizations are separated by thousands or tens of thousands of light years, conversation may be practically impossible even if everyone is trying. And then there is the explanation that Liu Cixin, one of the most celebrated science fiction writers of the 21st century, wove into his three-body problem trilogy. Published in China in 2008 and translated into English in 2015, Liu's second novel in the series, The Dark Forest, gave a name and a framework to an idea that had been circling around the scientific discussion for years: the dark forest hypothesis. The idea is this: the universe is like a dark forest, full of hunters, every one of them armed, every one of them moving silently, every one of them terrified. A civilization that reveals its location by broadcasting radio signals, by building structures visible from space, by in any way announcing its presence, risks being destroyed by whatever else is out there. Not because all civilizations are inherently aggressive, but because survival is the primary driver of any civilization, and because any sufficiently advanced civilization cannot afford to take the risk that another civilization might be a threat. The only safe strategy is silence. And so every civilization that survives long enough to figure this out goes quiet. The galaxy fills up with intelligent beings, all of them holding their breath, none of them daring to make a sound. Liu described it this way in the novel: the universe is a dark forest. Every civilization is an armed hunter stalking through the trees like a ghost, gently pushing aside branches that block the path and trying to tread without sound. It is a brilliant and disturbing image, and it offers a different kind of answer to the Fermi Paradox. Not that everyone is dead, but that everyone has learned to be invisible. And if that is true, humanity's decades of broadcasting radio signals, our Arecibo message beamed into space in 1974, our Voyager golden records drifting out of the solar system, our constant radio leakage from television and communications, all of it might be the cosmic equivalent of lighting a signal fire in a dark, dangerous wood. A beacon saying, "Here we are, come find us." Not all scientists find the dark forest hypothesis convincing, it should be said. It relies on some strong assumptions, particularly that resources are sufficiently scarce and technology sufficiently limited that destroying a potential competitor is always preferable to coexisting. A civilization advanced enough to cross interstellar space might have access to resources abundant enough that competition becomes irrelevant. But the hypothesis is taken seriously as one of several candidate explanations, and it is deeply unnerving in its internal logic. Let's talk about what we have actually found when we have gone looking, because we have been looking seriously and systematically for decades now, and the results are instructive, though not in the way we might have hoped. The SETI, Search for Extraterrestrial Intelligence program, has been operating in various forms since Frank Drake conducted the first formal radio search for extraterrestrial signals in 1960, a project he called Project Ozma, using the 85-foot radio telescope at Green Bank, West Virginia. Drake aimed his telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for any signals that seemed artificially produced. He found nothing, but the search had begun. In the decades that followed, SETI evolved and expanded. The logic behind listening for radio signals is simple and compelling. Radio waves travel at the speed of light, can cross enormous cosmic distances, and are relatively cheap to produce. Any civilization that developed radio technology for its own internal communication purposes would leak those signals into space, and a sufficiently sensitive receiver on another world might pick them up. Cornell University physicists Philip Morrison and Giuseppe Cocconi had laid the theoretical groundwork in a 1959 paper, speculating that any civilization trying to communicate across space might do so at the hydrogen line frequency, 1420 MHz, because hydrogen is the most common element in the universe, and its natural frequency would likely be familiar to any civilization that understood physics. The most famous moment in SETI's history came on August 15, 1977, when a project volunteer at Ohio State University's Big Ear radio telescope named Jerry Eman was analyzing data from the telescope's ongoing SETI observations. Something in the data caught his eye, a strong narrowband radio signal near the 1420 MHz hydrogen line that was unlike anything natural, a signal that lasted 72 seconds and then vanished. Eman circled it on the printout and wrote one word in the margin: "Wow!" And the "wow" signal, as it has been known ever since, became the best candidate for an extraterrestrial radio transmission ever detected, and has never been explained or detected again, despite numerous follow-up searches. In 2022, a paper identified 3 possible Sun-like stars at the coordinates where the WOW signal originated, including a star called 2-mass 192819882-2640123. Breakthrough Listen, the largest and most well-funded SETI program in history, launched in 2015 with $100 million in funding from Russian-born billionaire Yuri Milner, conducted a targeted search around that star using the Green Bank Telescope in West Virginia and the Allen Telescope Array in Northern California. They heard nothing. Breakthrough Listen itself represents an extraordinary commitment to the search. The project surveys the 1 million closest stars, the nearest 100 galaxies, the plane of the Milky Way, and the galactic center. It has ruled out the presence of powerful transmitters in over 140,000 background galaxies within the fields of view of its Green Bank Observatory observations. The null result from Breakthrough Listen does not prove no one is out there, but it constrains what kind of signals might be detectable, and it extends the silence further and further. Decades of SETI effort have produced nothing definitive, no confirmed signal, no repeating transmission, no evidence of intelligence anywhere in the universe except here, on this one small blue dot. That silence is not proof that we are alone, but it is data, and data has weight. There is a concept that bears on all of this, introduced by Soviet astrophysicist Nikolai Kardashev in a 1964 paper titled Transmission of Information by Extraterrestrial Civilizations. Kardashev was trying to think about what kinds of signals civilizations at different stages of development might produce, and to do that, he developed a framework for classifying civilizations by their energy consumption. A Type 1 civilization, in Kardashev's scheme, controls the entire energy output available to it from its home planet. All the sunlight, geothermal energy, wind, tides, everything the planet and its star contribute. Physicist Carl Sagan later refined the scale and placed humanity at approximately Type 0.7 on a logarithmic measure, meaning we are not even a Type 1 civilization yet. As of 2023, estimates put Earth at about 0.7276 on the Kardashev scale. Some estimates suggest Earth would become a Type 1 civilization around the year 2347, assuming continued growth in energy use, though transition to new energy technologies could accelerate this. A Type 2 civilization controls the entire energy output of its star, something on the order of 10 to the 26th power watts for a Sun-like star. Physicist Freeman Dyson famously described one way a civilization might achieve this: by constructing a sphere around its star, capturing all of the star's output directly. Such a structure, now called a Dyson sphere, would be visible from enormous distances, not as visible light, but as an anomalous infrared signature, waste heat radiating out from the sphere. Astronomers have actually looked for Dyson spheres. They have found some intriguing candidates over the years, stars with unusual dimming patterns, but nothing confirmed. A Type 3 civilization controls the energy output of an entire galaxy. Physicist Michio Kaku has estimated that with a 1% annual growth in energy use, humanity might reach Type 2 in about 3,200 years, and Type 3 in about 5,800 years. Those timescales seem long from a human perspective, but from the perspective of a universe that is 13.8 billion years old, they are nothing. A civilization that started just 1 billion years before us and grew at that rate would by now be operating at Type 3, visible from anywhere in the observable universe, radiating at galactic scales, impossible to miss. And yet we have detected no Type 2 or Type 3 civilizations anywhere. The universe, as far as our instruments can tell, is entirely populated by Type 0 civilizations, specifically by us. The sheer scale of what is absent, the missing empires, the missing megastructures, the missing galactic beacons, is almost incomprehensible. If the universe is 13.8 billion years old and civilizations can reach Type 3 within a few thousand years of developing technology, the universe has had billions of years to fill up with Type 3 civilizations. The fact that there are none, that we can see none, that every galaxy we examine with our best instruments shows no sign of being home to a civilization harnessing its entire energy budget. That fact demands an explanation. So where does all of this leave us? What does the silence of the universe actually mean? The honest answer is, we don't know, and the range of possibilities is extraordinary. At one end of the spectrum is the hopeful interpretation. The great filter is behind us. The hard part of getting to intelligence is over, and we are survivors in a mostly barren, but not necessarily threatening universe. We may be early, we may be rare, we may have billions of years ahead of us to expand and flourish. Robin Hanson himself and a team of colleagues once used a model called the Grabby Aliens framework to estimate that given the lack of visible alien civilizations in our sky, humanity may have arrived early to the universe, and that we might encounter the first expanding extraterrestrial civilizations somewhere between 200 million and 2 billion years from now. Not a problem for us or anyone alive today. At the other end is the terrifying interpretation. The great filter is ahead. The universe is a graveyard, not because intelligence never arose, but because every civilization that arose eventually destroyed itself, and we are looking at our own future in the silence around us. And in between those two poles are dozens of other possibilities. The zoo hypothesis, the dark forest, the argument that civilizations simply choose to go inward rather than outward, retreating into virtual realities, or engineered inner worlds rather than the hard work of expanding across space. The argument that interstellar communication is simply harder than we imagine, and that civilizations are out there, but isolated by the basic physics of the universe. Each of these possibilities has different implications for how we should be living, what we should be building, what we should be afraid of. And the science of the Fermi Paradox is not merely an abstract intellectual puzzle. It connects directly to the most practical questions humanity faces right now. Consider what it means if the great filter is the development of nuclear weapons and the inability to not use them. In that scenario, every technological civilization eventually reaches the point of nuclear capability, and almost every one of them, faced with the political pressures, the competitive dynamics, the tribal instincts that drove the evolution of intelligence in the first place, eventually uses those weapons in a way that ends the story. On our planet, the Bulletin of the Atomic Scientists has maintained what they call the doomsday clock, a symbolic measure of how close humanity is to self-inflicted catastrophe. In 2026, that clock sits at 85 seconds to midnight, the closest it has ever been to midnight in its history, set there by the Bulletin in recognition of nuclear risk, the climate crisis, and the increasingly rapid and ungoverned development of artificial intelligence. We have come close before. During the Cuban Missile Crisis in 1962, nuclear war between the United States and the Soviet Union was narrowly avoided, and on at least one occasion, due to a Soviet submarine officer named Vasily Arkhipov, who refused to authorize the launch of nuclear torpedoes when his submarine came under attack from American depth charges, and his captain believed they were already at war. One man's decision, in the pressure and darkness of a submerged submarine, may have prevented the end of civilization as we know it. That story should not make us comfortable. It should make us understand how thin the margin is between here and catastrophe. If that margin, that one person's call, that one moment of reason in a moment of panic, is what stands between a civilization and destruction, then it becomes comprehensible why civilizations might routinely fail to get through the nuclear phase. Not because the technology is inherently civilization-ending, but because the social and political structures that control it are imperfect, and imperfect systems, given enough time, will eventually produce the worst possible outcome. Consider what it means if the great filter is climate change, the systematic transformation of a planetary atmosphere that makes the conditions for complex life increasingly hostile. Civilizations that burn through their planet's stored carbon energy to build technology might routinely find, by the time they understand what they are doing, that the feedback loops they have triggered are too powerful to reverse. The atmosphere warms, the ice caps melt, sea levels rise, weather patterns shift, agricultural systems fail, water supplies diminish, and a civilization that might have found its way to the stars, instead, finds itself spending all of its energy and political capital managing a deteriorating homeworld until it can no longer sustain the complexity needed to maintain advanced technology. This is not a distant hypothetical. This is a trajectory that can be drawn on a graph using data that already exists. The carbon in our atmosphere is rising. The temperature is rising. The consequences are accumulating. Whether or not humanity successfully navigates this transition will depend on decisions being made right now, in this generation, by people who are alive today and who will be long dead before the full consequences of those decisions play out. The universe, if the great filter is climate change, is littered with worlds that got to exactly this point and made the wrong choices. Consider what it means if the great filter is artificial intelligence. This is the newest candidate, and in some ways the most intellectually dizzying, because we are in the process of creating artificial intelligence right now, and we genuinely do not know where it leads. The history of AI development has been characterized by repeated surprise. Capabilities that scientists assumed would take decades to develop have arrived in years or less, and the rate of progress shows no sign of slowing. Large language models, systems capable of holding sophisticated conversations and generating plausible text across essentially any topic, have gone from laboratory curiosities to ubiquitous tools within a few years. Systems capable of designing proteins, generating images, writing code, and performing tasks that previously required significant human expertise are already deployed at scale. What comes next is genuinely uncertain. Some researchers believe artificial general intelligence, systems that can match or exceed human performance across the full range of cognitive tasks, is decades away. Others believe it could arrive within years. The question of what such systems would do, whether their goals would be aligned with human flourishing, whether they could be controlled and directed, is one of the central open problems in AI research today. Garrett's 2024 paper in Acta Astronautica argued that even before superintelligent AI arrives, the weaponization of AI by competing groups within civilizations, using AI to gain military, economic, or political advantage over rivals, could destabilize civilizations before they have time to become multiplanetary. Once a civilization is confined to a single planet, it is vulnerable. One catastrophic event, whether natural or artificial, can end the story. The only real insurance against planetary catastrophe is being on more than one planet. And if AI development outpaces multiplanetary expansion, which Garrett argues it almost certainly does given the different resource requirements of the two projects, then civilizations face a window of vulnerability that they may not survive. The fact that Earth in 2026 is developing AI at a pace that is measured in months, while the earliest realistic scenarios for a human settlement on Mars are measured in decades, that gap is not merely inconvenient. It might be the gap that, in the cosmic story of civilizations, separates the ones that make it from the ones that don't. All of these potential filters share something. They all involve a civilization reaching a certain level of power, the power to transform its planet, to destroy itself, to build tools that exceed its wisdom, before it has developed the wisdom, the cooperation, the long-term thinking needed to manage that power safely. There is something almost tragically predictable about it. Evolution selects for intelligence, because intelligence helps individuals and groups compete for resources in the short term, but the skills needed to survive in the long term, coordination across generations, willingness to sacrifice present comfort for future security, cooperation with strangers and rivals, these are not the skills that evolution primarily rewards. They have to be built deliberately, through culture and institutions, and deliberate effort. The great filter, in this reading, might not be a single technological tripwire, but a developmental mismatch. Civilizations get powerful before they get wise, and the universe is full of the results. There is one more possibility that deserves serious attention, and it takes the question in a completely different direction. What if the universe is not empty? What if our methods of detection are simply wrong? We have been looking for civilizations like us, civilizations that use radio waves, that build structures at the scales of planets or stars, that consume resources in ways that produce detectable signatures. But what if advanced civilizations don't do those things? What if the trajectory of technological development leads not toward megastructures and radio broadcasts, but toward something much quieter, much smaller, much harder to detect? Physicist Freeman Dyson pointed out that a civilization advanced enough to build structures around its star might also be advanced enough to build computation at molecular scales, operating at temperatures just above absolute zero to maximize thermodynamic efficiency. Such a civilization would produce almost no waste heat, would be invisible to any ordinary astronomical survey, and might be indistinguishable from a background of cold matter to any observer who didn't know exactly what to look for. If advanced civilizations are quiet by nature, if the trajectory of intelligence leads toward efficiency and miniaturization rather than outward expansion and grand construction, then the silence of the universe says nothing about whether anyone is out there. They might all be there, surrounding us, using the universe in ways we haven't imagined yet. This possibility is sometimes called the transcension hypothesis, the idea that civilizations that survive long enough don't expand outward into space, but inward into complexity, building denser and denser and more efficient systems at smaller and smaller scales. It is hard to evaluate scientifically because it makes almost no testable predictions, but it offers a way out of the darkest versions of the Great Filter story. One of the most disquieting things about the Fermi Paradox, and the Great Filter specifically, is what it implies about the significance of a discovery. If we were to find, tomorrow, evidence of simple life on Mars, or on Europa, or on Enceladus, a microbe, a fossil, any trace of biology, the scientific world would celebrate. It would be the discovery of the century, possibly the greatest discovery in the history of science. And it would also be, in the logic of the Great Filter, bad news, very bad news. Because here is the chain of reasoning. If life exists on Mars, then life can arise independently on at least 2 rocky planets in the same solar system. If it can arise independently in our solar system, then it almost certainly arises routinely throughout the galaxy. If life arises routinely, then the filter that keeps intelligent civilizations rare is not the origin of life, it is something later. And something later means something that is waiting for us. Nick Bostrom, who has written perhaps more clearly about this than anyone, put it this way: the best news we could receive from Mars is that it is dead. Completely, sterilely, lifeless. No fossils, no organic chemistry beyond what has fallen there from space. Nothing. An utterly dead world. That emptiness would be good news. It would suggest that the filter is in the past, that the origin of life is genuinely hard, and that we are genuinely rare survivors. The dead world we don't want to see is a world with traces of ancient life, life that started and then stopped, life that almost made it. Bostrom's argument is not that we shouldn't look. We absolutely should look. The search for life elsewhere is one of the most important scientific endeavors of our time. But we should be clear about what we want to find and why we want to find it. And when it comes to the Great Filter, our preferences and the facts do not necessarily align. Let's think about what the Milky Way actually looks like from the perspective of a civilization trying to assess its chances. Our galaxy is roughly 100,000 light-years across and about 10 billion years old. It contains between 200 and 400 billion stars. Many of those stars are far older than our Sun. Some star systems in the Milky Way have been stable for 8, 9, or even 10 billion years, twice as long as our solar system has existed. If life is possible and intelligence is likely, there should be civilizations in this galaxy many times older than us. Not a little older, vastly older. Civilizations that had billions of years head start. Even at modest speeds, a small fraction of the speed of light, a civilization that started expanding 1 billion years ago could have reached every corner of the galaxy and back again. The numbers simply do not work unless something is stopping civilizations from doing this. Either they don't exist, or they don't expand, or they don't survive long enough to expand very far. The 3 basic options of the Fermi Paradox: we are rare, we are hiding, or we are temporary. And the evidence we have, the silence, the empty sky, the absence of megastructures and signals and visitors, is consistent with all 3 and discriminates between them poorly. Something happened somewhere in the universe that we will never know about. Civilizations rose and fell on worlds we have never seen and never will, around stars too distant for even our best telescopes to characterize as anything more than a point of light. They built things, they thought things, they looked up at their own versions of the night sky and wondered if they were alone. And then, something. The great filter doesn't care about the details. It doesn't care whether it was war, or disease, or climate, or a technological failure no one saw coming. All it cares about is the outcome. And the outcome, in every case we can calculate from the silence around us, was that no one made it to the stars and stayed there. No one left a signature large enough for us to see across the light years. That is an enormous weight to sit with. An entire universe of stories, of minds, of attempts and failures and near misses, all of it invisible and forever out of reach. The universe's graveyard is not a metaphor chosen for dramatic effect. It is, in the interpretation of the great filter that many scientists take most seriously, a literal description of what is out there. Not just distance separating us from other civilizations, but death. All those potential conversations, all those other ways of being conscious in a universe, silenced before they could reach anyone. But the story doesn't have to end there, because we are still here. We are still having this conversation. And the fact that the great filter is real, that something stops civilizations from persisting and expanding, doesn't mean it is inevitable. It means it is a challenge. It means it is something that can, in principle, be overcome. The researchers who study existential risk, the scientists, philosophers, and engineers who take the Fermi Paradox seriously and ask what it implies about our own situation, have identified a set of things that might matter. Becoming multiplanetary is near the top of nearly every list. A civilization spread across multiple worlds, multiple star systems, is vastly more robust than a civilization confined to a single planet. A pandemic that kills everyone on Earth doesn't kill everyone on Mars. A nuclear exchange that destroys Earth's atmosphere leaves the Mars colony intact. A rogue AI that turns Earth into paperclips has no jurisdiction over a human settlement around another star. Multiplanetary is not a guarantee of survival, but it is a form of insurance that fundamentally changes the odds. The transition to sustainable energy sources matters, because a civilization that destroys its planet's climate before it develops the technology to leave the planet has closed off its own future. The development of AI safety, the science of ensuring that advanced artificial intelligence systems pursue goals aligned with human flourishing, matters, because the alternative may be the end of the story. International cooperation on the management of nuclear arsenals, biological research, and emerging technologies matters, because many of the most dangerous scenarios involve competitive dynamics between nations or groups, and cooperation is the antidote to competition that ends in catastrophe. None of this is easy. Any observer of human history will find reasons for pessimism. The Great Filter story, read clearly, suggests that these challenges are very hard enough that no civilization before us, in the part of the universe we can observe, has successfully cleared them all. But hard is not impossible, and the fact that we know to look for the filter, that we have the scientific tools and the intellectual framework to understand what might be killing civilizations, gives us something that no previous generation of humans ever had: a map of the danger. There is a statement from the great astronomer Carl Sagan that feels especially appropriate here, given what we are discussing. Sagan said, "In the deepest sense, the search for extraterrestrial intelligence is a search for ourselves." He meant that looking for other civilizations tells us things about what it means to be a civilization, about what the long-term future of intelligence might be, about where the road goes if you keep walking it. The silence we find when we look out into the universe is not just data about space. It is data about us, about what we might become, about the challenges that intelligence faces everywhere when it rises from the slow churn of evolution into the hot, bright, dangerous capability to reshape the world around it. Every telescope we point at the sky, every radio dish we set to listening, every analysis of cosmic silence is a mirror. We are looking for other minds and finding absence, and that absence is a message. The message is not obviously comforting, but it is profound. It says, "This is hard. It has been hard for everyone who has tried it. Whatever is coming, the filter, the challenge, the great test of intelligence, it is hard enough that we have seen no one pass through it. And now, it is our turn. Let's do something a bit different for a moment and try to fully inhabit what it would mean if the optimistic interpretation is right. If the filter is behind us, if we are genuinely among the first or the rarest of intelligent civilizations, if the universe is not a graveyard but a nursery, very young still, just beginning to produce minds, in that case, we carry something extraordinary. The last 2 to 3 billion years of Earth's history, the long, patient unfolding of life from single cells to animals to mammals to primates to us, would have been extraordinarily lucky. We would be the product of a 1,000,000,000 to 1 shot, or longer odds than that. Every mass extinction that wiped out the competitors of our ancestors, every asteroid impact that reset the game, every evolutionary accident that led to the particular brain that eventually looked up at the stars and started asking questions, all of it would have had to go exactly right. And it did. Against all those odds, it did. That would make us not just rare, but precious. In a universe that is otherwise dark and silent and vast, it would mean that the thoughts you are having right now, the experience of listening to this, of following this argument, of feeling whatever you feel about the implications, that experience exists in a universe that might have gone billions more years without producing anything like it. Consciousness, here on this small planet, might be among the rarest things in the cosmos. Not a given, not a statistical inevitability, a miracle, or something that functions as a miracle, something so improbable that it is effectively unique. And if that is so, then what we do with it matters enormously. More than anything else in our history or politics or daily lives, the question of whether we survive matters. Whether we get through the great filter, whether it is the nuclear one, the climate one, the AI one, or something we haven't imagined yet, whether we become the civilization that makes it, is perhaps the most important question in the universe. Not metaphorically, literally. In a universe this empty, whether intelligence survives here might be the thing that determines whether intelligence persists anywhere in this galaxy for the next billion years. The astrobiologists Dirk Schulze-Markuch and William Baines spent years reviewing the history of life on Earth and studying the question of how likely the various steps toward intelligence actually are. Their conclusion was nuanced and in some ways reassuring. They found that several of the key transitions, oxygenic photosynthesis, the eukaryotic cell, multicellularity, and eventually tool-using intelligence, appear to be likely outcomes of evolution on any Earth-like planet, given enough time. These are not 1 in a trillion flukes, but things that evolution tends toward, given the right conditions, because they are adaptive enough that once a simpler version evolves, selection reliably pushes it forward. Their conclusion was that the most likely candidate for the Great Filter is either abiogenesis, the origin of life itself, or the inability of civilizations to settle other worlds, whether through self-destruction or simply running out of the resources and organizational capacity needed for interstellar expansion. It is either the beginning of the story or the end. Either we were extraordinarily lucky at the very start, or we are approaching the challenge that no one has beaten. Either way, the stakes are clear. Either the filter is the one we passed billions of years ago when the first molecule of RNA first managed to copy itself in a warm pool of primordial chemistry, or the filter is the one we are approaching now, in the 21st century, on a planet with nuclear weapons and accelerating AI, and a climate that we are reshaping in ways we don't fully control. The James Webb Space Telescope, launched on December 25, 2021, represents one of humanity's most ambitious attempts to understand the universe we live in, including the question of whether it hosts life elsewhere. Webb is capable of pointing at exoplanets, planets orbiting other stars, and analyzing their atmospheres for what scientists call biosignatures, chemical signatures that might indicate the presence of life. An atmosphere with high concentrations of oxygen and methane, for example, would be highly suggestive of biological processes, since these two gases react with each other chemically and would quickly disappear from an atmosphere without constant replenishment, which biological activity could provide. Webb has been examining the atmospheres of several candidate worlds, including those in the TRAPPIST-1 system, a red dwarf star about 40 light-years from Earth that hosts 7 rocky planets, 3 of which are in the star's habitable zone. The early results from Webb have provided data on some of these worlds' atmospheres, though no definitive biosignatures have yet been confirmed. The search continues, the data accumulates, And every null result, every world that turns out to be barren, adds another data point to the great filter argument, not confirming it, but making the silence of the universe a little harder to explain away. The next generation of telescopes, including what NASA has called the Habitable Worlds Observatory, would be capable of directly imaging Earth-sized exoplanets, not just detecting their atmospheric chemistry indirectly, but actually seeing the light from the planet itself, separated from the glare of its star. If such observations could be made of dozens or hundreds of habitable zone Earth-sized planets, and if the results showed no signs of photosynthesis, no oxygen atmospheres, no biosignatures of any kind, that would be strong evidence for the rare Earth hypothesis, strong evidence that the filter is behind us, and strong evidence that life, at least complex life, is genuinely rare. If instead those observations found oxygen atmospheres and photosynthetic signatures on many of the worlds observed, the implications would go in the opposite direction. Complex biology would turn out to be common, the filter would almost certainly lie ahead, and we would need to think very seriously about what that means. There is something almost unbearably poignant about all of this. The Fermi Paradox is, at its core, a story about loneliness, about a species that looks up at an incomprehensibly vast universe and finds it empty of voices. We have been broadcasting our presence for over a century now, not deliberately mostly, but as a side effect of every television station and radio broadcast and military radar and cell tower and satellite uplink that has ever been aimed into space, a spreading sphere of electromagnetic noise traveling outward from Earth at the speed of light, right now reaching the stars within about 100 light-years of Earth. The stars, we have been unknowingly announcing ourselves to include some of the most thoroughly studied star systems in the sky, and no one has answered. The children's book version of this story always has an answer coming. The radio telescope detects a signal. The contact is made. The long isolation ends. That's the story we want. The story that says we are not alone, that somewhere out there are other minds who have thought similar thoughts and found similar answers and are waiting to compare notes. It is a beautiful story, and it may even be true, but the universe, so far, has not provided evidence for it. Instead, what we have is this: a sky full of stars, each one potentially circled by worlds, and all of it apparently silent. A universe 13.8 billion years old that has had time to fill with intelligence 1,000 times over, and apparently hasn't. A paradox, named after a man who asked a simple question at lunch and died before it was answered. A hypothesis named for a filter that might be a test, a great, cosmic, impartial test that every civilization eventually faces, and the deeply uncomfortable possibility that the test is one that almost no one passes. We do not know where we are in the story. We do not know if we have already passed the hardest part, or if the hardest part is just ahead. We do not know if the silence around us is the emptiness of a universe just beginning to fill with life, or the stillness of a cosmic cemetery where the dreams of 1,000 civilizations have come to rest. What we know is this: we are here, we are awake, we are asking the question. And we have, at this moment in history, the opportunity to either confirm the worst interpretation of the cosmic silence by following every other civilization into whatever lies beyond the filter, or to do something that, as far as we can tell, no one else in the observable universe has managed to do: to look at the evidence, to understand the danger, and to choose differently. The great filter is not destiny, it is a pattern, and patterns can be broken. Every civilization that ever rose and fell on some distant world did so without knowing what we know. They did not have the benefit of the Fermi Paradox framing their situation. They did not know they were potentially following a pattern that had repeated itself across the universe, that the very silence around them was a warning. They just lived their lives, made their choices, built their weapons, burned their atmospheres, created their intelligence, and let whatever happened happen. We know differently. We can see the pattern. We can name the dangers. We can look at the doomsday clock sitting at 85 seconds to midnight and understand, with clarity that no previous generation of humans possessed, that the clock is not a metaphor but an argument about where a particular kind of civilization, armed with particular kinds of technology, tends to end up. And we can decide that the argument is not about us. That decision, if it is made, and made seriously, and followed through at the level of policy and technology and culture and cooperation, might be the most important decision any civilization has ever made, because it would not just be a decision about Earth's future. In a universe this silent, it might be a decision about the future of intelligence itself. Let's close with something that the astronomer Seth Shostak of the SETI Institute said about the project of searching for extraterrestrial signals. He acknowledged that one can postulate a galaxy filled with intelligent civilizations that simply have not colonized Earth and have not contacted us for any number of reasons. But he also noted something that cuts to the heart of the whole problem: the absence of evidence for alien megastructures, alien megascale engineering, alien transformations of galactic resources, any of the obvious signatures that a sufficiently advanced civilization would produce, is itself significant. It is not proof of absence, but it is absence of evidence. And absence of evidence, when you are looking hard enough in enough places, starts to become meaningful. We have looked, we have listened, we have pointed our best instruments at the sky and heard nothing that we can confirm as another voice. And we have built a framework, the Fermi Paradox, the Great Filter, the Kardashev Scale, the Drake Equation, that lets us think clearly about what that silence might mean. The framework does not give us the answer, but it tells us what the answer might look like, and it tells us what is at stake. What is at stake is enormous, not just our own survival, though that is certainly enormous, but the larger question of whether intelligence, the capacity for reflection, for wonder, for asking questions about the universe and beginning, however haltingly, to answer them, whether intelligence has a future in this cosmos, or whether it is, as the silence suggests it might be, something that arises, struggles briefly, and then flickers out, leaving the universe as dark and quiet as it found it. We are, right now, the only civilization we know of that is asking this question. We are looking at a universe full of stars and finding it empty of others like us, and we are trying to figure out why. That act of inquiry, that refusal to simply accept the silence and stop listening, is itself a form of hope. It says, we are not done, we are not going quietly, we are asking what it takes to survive, and we are listening for the answer. The universe may be a graveyard, but we are still alive in it, and what we do next is the question that may matter more than any other question our species has ever faced. If any of this found its way into a part of your mind that is still thinking about it, the silence, the filter, the weight of what the empty sky might mean, then do me one favor before you close this out. Share this with someone who needs to think about it too, not because the ideas are comfortable, but because understanding the challenge is the first step to meeting it. And leave a comment below with what you think. Is the filter behind us, or is it ahead? That question is one of the most important questions of our time. Come be part of the conversation. Let's go deeper into the mathematics of the situation, because the numbers involved in the Fermi Paradox are so extreme that they deserve more than a passing mention. They deserve to be sat with, turned over, examined from multiple angles, because the moment you really absorb them, the paradox stops being an intellectual curiosity and starts being something that vibrates at a much lower, more unsettling frequency. Start with time. The Big Bang happened 13.8 billion years ago. The first stars formed roughly 100 to 200 million years after that, and the first generation of stars were very different from the stars we see today. Enormous, hot, burning through their fuel in a few million years rather than billions. And when they died, they seeded the interstellar medium with the first heavy elements: carbon, oxygen, nitrogen, silicon, iron. The elements that life as we know it is made of. Without those first-generation stars dying and scattering their contents into space, there could be no rocky planets, no water, no organic chemistry, no biology. So there is a delay built into the story. Life cannot begin until the universe has had time to produce the raw materials for it. That delay is on the order of 1 billion years or so. But after that initial delay, the universe has been capable of hosting life for something like 12 to 13 billion years. Long enough for a civilization to have arisen, collapsed, arisen again in some other form, collapsed again, and gone through the whole cycle dozens of times. Long enough for a civilization that survived its own great filter to have colonized not just its own galaxy, but multiple galaxies, spreading at even 1% of the speed of light. The absence of any evidence of that expansion is not a small absence. It is a staggering, almost incomprehensible absence. It is the absence of everything that should, by the numbers, have happened. Carl Sagan grappled with this directly in his book Cosmos and in his television work. One of his central commitments was to the idea that the universe is so large, so old, so full of stars and planets and possibilities, that the emergence of intelligence must have happened many times. Sagan put the estimate at 1 million advanced civilizations in the Milky Way alone, a figure he arrived at in 1974 by working through the Drake equation with a particular set of assumptions. He was not cavalier with numbers. He was one of the most scientifically rigorous popular science writers who has ever lived. And that figure of 1 million civilizations represented his genuine best estimate given what was known at the time. 1 million civilizations in one galaxy of 2 trillion galaxies. The mind cannot really contain what that would mean. Not just radio signals overlapping and crisscrossing the galaxy, but an absolute saturation of intelligence. Civilizations thousands of years older than us, Type 2, Type 3, having long since solved every problem that seems intractable to us right now, and yet nothing. No signal that holds up to scrutiny. No structure that requires an intelligence to have built it. No colonization front rolling through the galactic arm where our solar system sits. The numbers are so extreme on both sides, so many opportunities for life, so complete an absence of evidence, that one of them has to be wrong. Either the opportunities are far less than they seem, meaning life is extraordinarily rare, or the civilizations that arise routinely fail to persist, fail to expand, fail to leave any trace. These are not the only 2 options, but they are the 2 that most naturally emerge from the math. One of the most philosophically rich aspects of the Great Filter discussion is how it changes our relationship to the search for extraterrestrial life. Scientists who work in astrobiology, the study of the origin, evolution, and distribution of life in the universe, tend to be optimistic people. They go into the field because they find the prospect of life elsewhere compelling and exciting. The idea that microbial life might exist on Mars, or in the subsurface ocean of Europa, one of Jupiter's moons, where a liquid water ocean is believed to exist beneath the ice, or in the atmosphere of Venus. These ideas are not science fiction for astrobiologists. They are working hypotheses that drive real research programs. And yet the Great Filter framework puts these scientists in an uncomfortable position. If astrobiology is successful, if we find life on Mars, or in the plume of water vapor erupting from Enceladus, one of Saturn's moons, or in the warm seas beneath Europa's ice, the scientific community will need to grapple very carefully with what that discovery means in the context of the Fermi Paradox. The key question is not just whether life exists elsewhere, but how independently it arose. If the microbial life on Mars turns out to be genetically related to life on Earth, sharing the same basic biochemistry, the same DNA code, then there is a decent chance it didn't arise independently at all. It may have been transported. Rocks are regularly ejected from planets during asteroid impacts with enough force to escape the planet's gravity, and these rocks, carrying any organisms living within them, can drift through space for millions of years before being captured by another planetary body's gravity and falling to the surface. This process is called lithopanspermia, and it is not merely theoretical. We have meteorites on Earth that originated on Mars, and we know that some bacteria can survive the radiation doses and temperature extremes of space travel for extended periods within a protective rock. If life on Mars and life on Earth share a common origin, if one seeded the other, then finding life on Mars doesn't actually tell us that life arose independently in our solar system. It tells us that life, once it arises, is resilient and spreadable. Important, but not the same information. The game-changing discovery would be life on Mars, or on Europa, or anywhere else in the solar system that is genuinely biochemically distinct, using different amino acids, or a different nucleic acid code, or some other fundamental biochemical architecture that makes it clear it arose completely separately from Earth life. That would be astonishing. That would tell us that life is not just a one-time lottery win on a lucky planet, but something that chemistry reliably produces when the conditions are right. And it would immediately push the Great Filter toward the later stages, toward intelligence and technology and the social and political challenges of an advanced civilization, and away from the origin of life itself. Nick Bostrom articulated this most clearly. The discovery of independent life elsewhere in the solar system would be, in his words, both the most wonderful and the most terrible discovery in human history. Wonderful because it would confirm that life is a basic feature of the cosmos, not a freak accident. Terrible because it would tell us, by the logic of the Great Filter, that civilizations very routinely arise and very routinely collapse before leaving any detectable trace on the universe. Let's talk about what a truly advanced civilization would actually look like from the outside. This is not a trivial question, because our assumptions about what detectable alien civilizations would look like might simply be wrong, and that wrongness might explain the silence. Our radio searches are based on the idea that alien civilizations would use radio waves for communication, and that their radio emissions would leak into space. This seemed like a reasonable assumption in the 1960s and 1970s when the search began, because radio technology was what we had, and we were leaking enormous quantities of it into space already. The first powerful television broadcasts from Earth have been traveling outward at the speed of light since the mid-20th century, forming an expanding sphere of electromagnetic noise that by now has reached hundreds of star systems. If any civilization within about 80 to 100 light-years of us has sensitive enough radio receivers, they could in principle be picking up our old television broadcasts right now. But here is the thing. We are already moving past the radio era ourselves. Fiber optic cables carry most of our long-distance communications now. Satellite communications have become more directional and efficient. We are producing less electromagnetic leakage into space than we were 40 years ago, not more. A civilization that has been technologically advanced for even a few hundred years longer than us might produce essentially no detectable radio leakage at all, having transitioned to more efficient communication technologies that keep signals tightly beamed and contained. And this raises a genuine question about SETI's methodology. If even we are becoming electromagnetically quieter as we advance, why would we expect older, more advanced civilizations to be loud? The window during which a civilization is electromagnetically detectable from space might be very narrow, a few centuries at most, before efficiency and directed communication replaces the omnidirectional broadcast. In the context of cosmic time, a few centuries is nothing. It is far too narrow a window for any other civilization to randomly be pointing their receiver at us during the exact period when we are broadcasting, unless we also happen to be within that civilization's systematic survey area and within the limited distance that our leakage signals can be detected at all. The question of what would make a civilization detectable over cosmological distances is actually deeply interesting. Radio leakage fades too quickly. The inverse square law means that the power per unit area of a radio signal drops as the square of the distance, and even our strongest deliberate transmissions would be undetectable at the distance of the nearest star with any antenna we could realistically build. But there are other things that might be detectable across much larger distances. Waste heat. This is the key insight behind the Dyson sphere concept. Any civilization using large amounts of energy has to dump waste heat somewhere, and in space, the only way to dump heat is to radiate it as infrared light. A civilization that has wrapped its star in a shell or swarm of solar collectors would radiate heat at temperatures characteristic of the structure's surface, typically in the infrared range, and this infrared signature would be potentially detectable with sensitive enough telescopes across interstellar and even intergalactic distances. Astronomer Freeman Dyson proposed this in 1960, and since then, it has become one of the standard things astronomers look for when they are searching for evidence of advanced civilizations. The most famous episode in this search was the case of Tabby's star, officially known as KIC 8462852, located about 1,470 light-years from Earth. Beginning in 2015, this star captured global attention when it was found to display extremely unusual dimming patterns, irregularly spaced and shaped dips in brightness that don't match any natural explanation proposed for ordinary stars. Early media coverage floated the possibility that the dimming could be caused by a Dyson swarm, a collection of large megastructures in orbit around the star, blocking varying amounts of its light as they passed between the star and Earth. The scientific community was appropriately cautious, noting that natural explanations, dust clouds, cometary debris, were more likely. Subsequent analysis found evidence consistent with dust as the culprit, not megastructures. But the episode illustrated both the scientific excitement of the search and the care required in interpreting ambiguous data. Beyond Tabby's star, systematic searches for anomalous infrared sources, stars that produce more infrared light than expected for their spectral type, which might indicate they are partially enclosed in heat-radiating structures, have found some intriguing candidates but nothing definitive. The sheer number of stars that need to be examined is enormous, and the task of distinguishing natural infrared sources from artificial ones is genuinely difficult. The search continues, but it has so far produced no confirmed megastructure, no confirmed Dyson sphere, no confirmed evidence of any Type 2 or Type 3 civilization anywhere in the observable universe. Planetary scientist and science communicator Neil deGrasse Tyson has pointed out something important about the entire Fermi Paradox discussion: the assumption that advanced alien civilizations would necessarily want to communicate with us, or would have the inclination to colonize space in the way our science fiction envisions, may simply be wrong. Intelligence does not require the drive for exploration and expansion. Many intelligent species on Earth are not notably expansionist. Octopuses, which have remarkably sophisticated problem-solving abilities, are solitary, sedentary, short-lived, and have shown no signs of developing technology despite their intelligence. Intelligence, in other words, is a cognitive capability, and the uses to which it gets put depend on the particular evolved psychology of the species that possesses it. What if the most common form of intelligence in the universe is not expansionist and competitive, as human intelligence has been historically, but contemplative, curious, and self-contained? What if many of the civilizations that have arisen chose to direct their intelligence inward, into philosophy, mathematics, art, the exploration of the mind itself, rather than outward into the hostile environment of interstellar space? Such civilizations might leave essentially no trace detectable from Earth. They would be there, thinking, creating, experiencing, but they would be doing it quietly, on their own worlds, having decided that the cosmos is something to contemplate rather than to colonize. This is the essence of what some theorists call the quiet civilization solution to the Fermi Paradox. It doesn't require catastrophe. It doesn't require filters. It just requires that the particular configuration of drives and motivations that led humanity toward expansion and exploration is not universal, that there are many possible stable endpoints for a technological civilization, and only some of them involve reaching for the stars. Seth Shostak of the SETI Institute has acknowledged this possibility, but also pointed out its limitation as an explanation. It only needs one civilization to be different. If even one civilization among the thousands or millions that should have arisen chose to expand, the entire galaxy would be colonized. The quiet civilization explanation requires not just that most civilizations are quiet, but that every single one of them is, with no exceptions, ever, across 13 billion years of cosmic time. That's a hard constraint to satisfy. Let's think about the question of self-destruction in more specific, historical terms. Because it's easy to talk about civilizations destroying themselves in the abstract, but harder and more sobering to look at the actual trajectory that brought us to the specific dangers we face right now. Humanity's capacity for self-destruction was qualitatively different before the mid-20th century than it was after. Before the development of nuclear weapons, even the most devastating wars, and wars have been devastating throughout human history, were bounded in certain ways. They destroyed specific cities, specific regions, specific populations. They did not threaten the entire species. The Black Death killed perhaps a third of Europe's population in the 14th century, one of the worst demographic catastrophes in recorded history, and humanity recovered. The world wars killed tens of millions of people, reshaped the map of the world, and ended the assumptions of Western civilization about the permanence and security of civilization itself, and humanity recovered. Bad as these events were, they did not pose an extinction-level risk. The Trinity test on July 16, 1945, changed that. For the first time in human history, a single weapon could destroy an entire city, and within a few decades, human beings had built and deployed enough of these weapons to destroy every major city on Earth multiple times over, producing a nuclear winter that could collapse global agriculture and kill the vast majority of the human population. That capability, once it existed, could not be uninvented. It could only be managed, contained, deterred, slowly reduced, all of which require sustained political will, international cooperation, and the absence of catastrophic mistakes over the entire future of human civilization. The requirement is not that we never make mistakes. The requirement is that we never make the one specific kind of mistake that triggers the weapon exchange, that triggers the nuclear winter. That has to be true for not just decades but centuries, millennia, however long it takes to either eliminate the weapons or develop the multi-planetary insurance that makes a single-planet catastrophe survivable. The narrow escapes are instructive here, and they deserve more than a passing mention. The Cuban Missile Crisis of October 1962 brought the United States and the Soviet Union to the brink of nuclear war, when Soviet nuclear missiles were discovered in Cuba, and the Kennedy administration ordered a naval blockade. For 13 days, the world held its breath. What is less known is that at the height of the crisis, a Soviet submarine called B-59 was operating in the waters near Cuba, cut off from radio communication with Moscow, under attack from American depth charges that its crew did not realize were practice charges meant to signal it to surface. The submarine's captain, believing they were already at war, prepared to launch a nuclear torpedo. Under Soviet protocol at the time, a launch required the agreement of 3 officers. 2 agreed. The third, Vasily Arkhipov, a flotilla commander who was on the submarine, refused to authorize the launch. The torpedo was not fired. Nuclear war was averted by the decision of one man in a submarine, acting under extraordinary pressure without complete information. In 1983, Soviet early warning satellites detected what appeared to be a nuclear missile launch by the United States. The duty officer at the Soviet Early Warning Command Center, a lieutenant colonel named Stanislav Petrov, had to decide, in minutes, whether to report an attack to superiors who would almost certainly have ordered a retaliatory strike. Petrov decided the alarm was a false positive, based partly on the small number of missiles detected. He reasoned that a genuine US first strike would involve many more missiles simultaneously, and he reported a system malfunction rather than an attack. He was right. The alarm was indeed a false positive, caused by a satellite detecting the sun's reflection off clouds. But if Petrov had followed the official protocol and reported an attack, the Soviet retaliation might have launched. These are just 2 episodes we know about. Given the secrecy around nuclear command systems, the full history of near misses may be considerably longer. And the lesson is disturbing. The survival of civilization at specific moments in history has depended on the correct judgment of specific individuals operating under pressure, without complete information, with everything on the line. The probability that every such situation, over an indefinite future, will be resolved correctly approaches 0 as the time extends. Which is why the great filter version of nuclear weapons is not that a civilization deliberately destroys itself, but that maintaining the safety of the most dangerous technology indefinitely, without any institutional failure, without any war, without any catastrophic accident, is a standard that no civilization can be confident of meeting forever. The climate change version of the Great Filter operates on longer timescales and involves a more gradual transition, but the basic logic is similar. Every civilization that discovers fossil fuels, and fossil fuels are a natural product of any oxygen-bearing planet that has had abundant plant life for long enough, gains access to an enormous store of energy that enables rapid industrial development. The Industrial Revolution in England and then across Europe and North America from the late 18th century onward is a model for what this transition looks like. Rapid increase in energy consumption, rapid urbanization, rapid technological development, and as a side effect, the release into the atmosphere of carbon dioxide that had been stored in organic material for hundreds of millions of years. The problem is not that this is a bad deal. In the short term, fossil fuel energy is an extraordinarily good deal. It enables agriculture at scale, manufacturing, medicine, transportation, communication, all the things that have made the past 2 centuries of human civilization remarkable in terms of material well-being. The problem is that the consequences of burning fossil fuels are delayed. The carbon dioxide you release today will be warming the atmosphere for centuries. The temperature increases you trigger today will play out over decades and centuries. The feedback loops, methane released from thawing permafrost, ice loss reducing Earth's reflectivity, ocean absorption of heat changing weather patterns, take time to develop. A civilization might not even understand what it is doing until it has already committed itself to a trajectory that is very hard to reverse. And here is the specific way this might function as a filter. The technological development enabled by fossil fuel energy creates the social and political complexity that makes transitioning away from fossil fuels very difficult. The industries, the jobs, the economic structures built on fossil fuel energy become entrenched. The political systems that grew up alongside those industries resist the changes needed to shift to cleaner energy. The same intelligence that figured out how to extract and burn fossil fuels is now required to figure out how to stop. But it is now operating under the constraint of political systems, economic pressures, and short-term thinking that slow the response. A civilization might successfully develop the renewable energy technology, the storage technology, the grid technology needed to replace fossil fuels, and still fail to deploy it fast enough because the social and political machinery for making collective decisions is slower than the physics of atmospheric warming. If this is the filter, it means civilizations that develop fossil fuel energy tend to trigger changes to their planetary atmosphere before they develop the social technology needed to coordinate a transition away from fossil fuels. And the civilizations that manage the transition might be those with unusually good coordination mechanisms, or unusually coherent political structures, or perhaps just lucky timing in how quickly the consequences of their fossil fuel use became apparent. There is an argument about the Great Filter that doesn't receive as much attention as it deserves, which is the possibility that the filter is not a single event or a single challenge, but an accumulation of challenges, any one of which could end a civilization if all the others are successfully navigated. This is sometimes called the gauntlet model. You don't fail because of one filter, you fail because there are many filters, and each one reduces the probability of survival, and the cumulative probability of making it through all of them is very low. In this model, nuclear weapons are one gate, and most civilizations that develop nuclear weapons eventually destroy themselves with them. Climate change is another gate. Biotechnology, the potential to engineer pathogens or other biological agents capable of causing civilization-ending pandemics, is another gate. Artificial intelligence is another gate. The consolidation of political power by authoritarian regimes, empowered by surveillance technology, is another gate. Each of these challenges might individually be survivable. Civilizations might get through the nuclear weapons challenge a reasonably large fraction of the time, and might get through the climate change challenge a reasonably large fraction of the time. But when you multiply the survival probabilities together, the fraction of civilizations that make it through all of the gates might be very small. Nick Bostrom's formulation captures this in a general way. There are enough potential filters, and they are each difficult enough to navigate, that when you take the product of the probabilities of successfully navigating each one, the result might be consistent with what we observe. A universe that appears to have produced no surviving interstellar civilizations, despite abundant opportunities. Not because any single challenge is necessarily civilization ending, but because the combination of all of them, over time, tends to be. This model is in some ways more frightening than the single filter model, because it is more diffuse. Against a single filter, you can in principle focus all of your civilization's attention and resources on that specific challenge. Against a gauntlet of filters, you have to handle many serious threats simultaneously, maintaining safety and stability while navigating multiple parallel dangers. This is exactly the situation humanity finds itself in right now, simultaneously managing nuclear weapons proliferation, the acceleration of climate change, the governance of artificial intelligence, the risks of engineered pandemics, the fragility of global supply chains, and the political instability that comes when technological change outpaces social and institutional adaptation. Let's think about what it would actually take to pass through the gauntlet. What does the civilization on the other side of the Great Filter look like? First, it probably has to be genuinely multiplanetary, not in the science fiction sense of having a few research stations on Mars, but in the sense of having self-sustaining populations on multiple worlds, populations that could persist and eventually re-establish contact and connection if the homeworld suffered a catastrophe. The threshold for this kind of multiplanetary insurance is high. A Mars colony of 1,000 people that depends on resupply from Earth is not insurance, because if Earth collapses, the Mars colony collapses too. Real insurance requires a population large enough to be self-sustaining, with sufficient genetic diversity, technical knowledge, and industrial capacity to maintain and expand technology independently. Estimates for the minimum population size for a self-sustaining interstellar colony, the smallest group that could maintain genetic diversity and technological complexity over the long term, tend to run into the tens of thousands at minimum, and more conservatively, the hundreds of thousands or millions. Getting that many people off a single planet and to another world is an extraordinary engineering and logistical challenge, requiring energy inputs, launch infrastructure, and transportation technology far beyond what currently exists. Projections based on current trajectories suggest a first human landing on Mars might happen in the late 2030s, but a self-sustaining Mars colony is likely decades or centuries beyond that. Second, the civilization on the other side of the Great Filter has probably found a way to align its long-term interests with its short-term behavior. This is a governance and cultural challenge as much as a technological one. The problems that threaten civilizations, nuclear weapons, climate change, AI misalignment, all involve sacrificing present ease or advantage for future security. This kind of long-term thinking runs against the grain of evolutionary psychology, which was shaped by environments where the immediate threat was the relevant threat and the future was uncertain enough that discounting it heavily was a reasonable survival strategy. Passing through the filter might require cultural and institutional evolution as significant as any technological advance. The development of political systems capable of representing the interests of future generations, of economic systems that price long-term sustainability rather than short-term extraction, of social norms that treat the continuation of civilization as a responsibility rather than an assumption. These are not small changes. They represent a qualitative transformation in how a civilization thinks about itself and its relationship to time. Third, the civilization on the other side probably had the fortune, or the wisdom, to not make any irreversible mistakes during the vulnerable window, not to use the nuclear weapons once they had them, not to push the climate system past the tipping points that make recovery impossible, not to deploy superintelligent AI before having any meaningful ability to ensure its goals were aligned with civilization's survival. The window of vulnerability is finite. Civilizations become more robust as they become more distributed, as they spread off their home world, as they develop the redundancy and adaptability to survive a range of catastrophic events. But during the window, the margin is thin. One catastrophic mistake, one uncontrolled escalation, one deployment of technology before the wisdom to govern it is in place, and the story ends. There is something in the human spirit that resists the dark interpretation of the cosmic silence. We look up at those billions of stars, and we want to believe that somewhere out there, life has found a way, that we are not as alone as the silence suggests. That impulse is not irrational. It is an expression of something deeply embedded in our psychology, the drive to connect, to belong to something larger than ourselves, to not be the only ones. Carl Sagan understood this. His entire career was a testament to the human longing to be part of a larger story, a universe that contains not just stars and planets, but other minds, other ways of being conscious, other perspectives on the beautiful, terrible, improbable fact of existence. And maybe that impulse is right. Maybe we simply haven't been looking long enough, in the right ways, with the right tools. Maybe the wow signal of 1977 was exactly what it seemed to be when Jerry Amon wrote his one-word annotation on that printout, and we simply haven't found the source because we haven't been systematic enough or sensitive enough in our search. Maybe Breakthrough Listen, with its sweep of the million nearest stars and its analysis of the nearest 100 galaxies, will find something in data that hasn't yet been analyzed. Maybe the James Webb Space Telescope will detect an oxygen atmosphere on a planet in the TRAPPIST-1 system that cannot be explained by any non-biological process, and the whole question will immediately become much more concrete. Maybe the next telescope generation will find a dozen such worlds, and the universe will suddenly seem much less empty than it does today. These are genuine possibilities, not wishful thinking, but real scientific scenarios, with real probabilities attached to them, even if we can't estimate those probabilities precisely. The search is young, the technology is improving, the universe is large, and has had a long time to produce complexity, and our window into it has been narrow. But the silence so far is real too. The decades of listening, the surveys, the careful analysis of candidate signals, the null results, these are real data. The universe is not, as far as we can tell with the tools we have, loud with the transmissions of advanced civilizations. Whether it is quiet because we are looking wrong, or quiet because there is nothing to find close enough for us to hear, or quiet because something keeps happening to everyone who tries to make noise, that question remains open. One of the most haunting aspects of the Fermi Paradox is its temporal dimension. We are not just asking where all the aliens are. We are asking where all the alien ruins are. We are asking where all the evidence is that civilizations arose, flourished, reached for the stars, and left something that persists. Even civilizations that destroyed themselves might be expected to leave traces, anomalous atmospheric signatures on their home worlds, megastructure remnants, patterns in the distribution of heavy elements around their stars. We look, and we find nothing that requires an intelligent cause to explain. The timescales involved make this even more striking. Stars like our Sun burn for about 10 billion years. Rocky planets form within a few 100 million years of a star forming, and life, if it arises, has the entire remaining stellar lifetime to evolve. A civilization that arose on a planet orbiting a star that formed 5 billion years before our Sun, a star that has since burned out and gone cold, might have had billions of years of technological development before we even existed. What would a civilization billions of years more technologically advanced than us look like? What would it have built? What marks would it have left on the galaxy? The physicist John von Neumann proposed in the 1940s a concept now called a von Neumann probe, a self-replicating robotic spacecraft that could travel to another star system, use local resources to build copies of itself, and send those copies on to the next star system, and so on, spreading through the galaxy exponentially. Even with relatively slow travel, say 1% of the speed of light, such a probe network could spread through the entire Milky Way in about 300 million years. That's roughly the time since the first large land animals evolved on Earth. It is a cosmological eye blink. A civilization that launched such a program millions or billions of years ago should have probes everywhere by now. Everywhere, including our solar system. We have not found them. We have not detected any anomalous objects in the solar system that couldn't be explained by natural processes. The absence of alien von Neumann probes in our solar system, the absence of alien anything in our solar system, is a specific, measurable fact that bears on the Fermi Paradox. Either the probes were never built, or they were built and have missed us, or they are here, but we haven't recognized them as artificial. None of those options is particularly comforting. The Fermi Paradox turns out to be not one paradox, but several, layered on top of each other. There is the paradox of the missing signals. Why have radio searches found nothing? There is the paradox of the missing colonists. Where are the von Neumann probes? Where are the expanding civilizations? Where is the colonization front? There is the paradox of the missing megastructures. Why do we not see Dyson spheres, or stellar engines, or any of the other massive engineering projects that a Type 2 or 3 civilization might undertake? And underlying all of these is the meta-paradox. The universe is so large and old that any one of these absences, individually, might be explainable. But all of them simultaneously, across all of observable space and time? That convergence of absence is the thing that demands an explanation. Stephen Webb, in his book, If the Universe is Teeming with Aliens, Where is Everybody?, catalogued 50 different proposed solutions to the Fermi Paradox. 50. The sheer number of proposed explanations is itself a kind of answer. We don't know. We genuinely, honestly, deeply don't know. And the honest acknowledgement of that not knowing is the starting point for taking the question seriously enough to actually matter. What should we do with all of this? What are the practical implications of a universe that might be a graveyard, of a great filter that might be ahead of us, of a silence that might be a warning? The researchers at the Oxford Future of Humanity Institute, the Cambridge Centre for the Study of Existential Risk, and the Long Now Foundation, among others, have devoted serious intellectual resources to exactly this question. Their answers tend to converge on a set of priorities: existential risk reduction, multiplanetary expansion, AI safety research, pandemic preparedness, and the development of robust governance systems capable of managing transformative technologies. These are not just abstract academic priorities, they are responses to a concrete possibility that the universe has repeatedly produced civilizations at our level of development, and those civilizations have repeatedly failed to persist. If that possibility is taken seriously, the response is not despair, but clarity. Clarity about what matters, what the real priorities are, what kind of civilization we need to become to make it through the filter, rather than becoming another data point in the silence. Robin Hanson's original essay, written in 1996, ended on exactly this note. He acknowledged that where the filter lies is uncertain, but he argued that the question of what humanity should do in response to that uncertainty is not. We should work to understand the most likely locations of future filters. We should take the existential risks, nuclear weapons, climate change, biotechnology, artificial intelligence, as seriously as they deserve to be taken, which is very seriously indeed. We should work toward becoming a multiplanetary civilization, not as a science fiction aspiration, but as a genuine existential insurance policy. And we should do all of this with the understanding that we might be navigating a challenge that has ended every other civilization that has faced it. That is a sobering calling, but it is also, in its way, a magnificent one. We are the civilization on the edge of the filter. We are the ones who know it is there, and knowing it is there is the beginning of having a chance to make it through. Late at night, when the house is quiet and the sky is clear, sometimes you can go outside and really look up. Not a glance, not a casual survey. Actually look up, for long enough that your eyes adjust and the stars stop being a backdrop and start being what they actually are. Billions of individual suns, each one perhaps circled by worlds. Each world perhaps home to something. The feeling this produces is hard to name. It is not quite wonder, not quite loneliness, not quite awe. It is all three at once, and something more, a sense of the weight of the question, the enormous importance of what happens here, on this small world, in this galaxy full of silence. We carry something, all of us alive right now, that no previous generation of humans carried. We carry the knowledge that the universe is vast enough and old enough to have filled itself with intelligence, and didn't. We carry the knowledge that this silence might be a warning, a message from every civilization that failed to get through what we are about to face. We carry the responsibility that comes with being, as far as we know, the only species anywhere that is asking these questions and potentially capable of answering them with choices. That responsibility is heavier than it looks from the inside of any ordinary day. It gets lost in the noise of politics and economics and the 10,000 small urgencies that make up a life. But it is there, underlying everything, as surely as the stars are there behind the daylight. The question Enrico Fermi asked at that lunch table in 1950, "Where is everybody?" is still unanswered. And the answer, when it comes, if it comes, will tell us everything about the universe, about what it means to be intelligent, and about whether intelligence, in this particular part of the cosmos, at this particular moment in time, has a future. The universe may be a graveyard, but we are still alive in it, and we are still asking why. There is one more angle worth examining carefully, because it connects everything we've explored and lands on something concrete, something you can actually feel rather than just intellectually process. And it starts with a simple question: what does the great filter feel like from inside a civilization? From the inside, a civilization approaching a filter doesn't generally know it's approaching one. The Cuban Missile Crisis, looking back from now, was clearly one of the most dangerous moments in human history, a narrow passage through which civilization almost didn't come. But from inside October 1962, the people living through it had no idea they were a coin flip away from the end. They were scared, yes, the fear was real and present, and the public understood that something terrifying was happening. But they went to work in the morning. They made dinner. The rituals of ordinary life continued alongside the possibility of extraordinary catastrophe, and the resolution, when it came, felt like a return to normalcy rather than recognition of a survived crisis. 2 years later, the world was essentially back to its regular patterns, the near miss largely forgotten in the press of ordinary events. This is probably what every near miss feels like from inside. The people who almost destroyed themselves don't quite realize how close they came. The data showing that nuclear weapons protocols failed or nearly failed, at specific documented moments, is classified or buried in archives for decades. The feedback that would allow a civilization to understand we almost didn't make it is systematically delayed and obscured by the very social and institutional processes that make collective action difficult in the first place. If the great filter is behind a civilization that survived it, the survivors might not know they survived. They might not be able to point to the specific moment where the coin could have gone the other way and say, this was the filter. This was the thing that killed everyone else. And if you can't identify it, you can't systematically work to ensure you don't stumble into it again. This is part of why the study of existential risk, the serious academic and policy examination of the specific ways civilizations might destroy themselves, is so valuable and so undervalued. It is the attempt to identify the filter before you hit it, to see the pattern from outside rather than only experiencing it from inside when it's too late. The philosopher Derek Parfit wrote extensively about what he called the profound importance of humanity's present moment. Not important in the way that any given year feels important to the people living through it, but important in the deep sense that the decisions made in the current period of human history will have consequences extending across millions or billions of years, because the decisions we make now about technology, governance, and survival will determine whether there is anyone in the future to make decisions. Parfit called this the most critical stage in humanity's development, and he argued that the expected value of getting through this stage successfully, in terms of all the future lives and experiences and possibilities that would follow, dwarfs essentially everything else. Nick Bostrom has taken this argument further with what he calls the importance of existential risk reduction. A civilization that survives and eventually spreads through even a fraction of the galaxy has the potential for an almost incomprehensible amount of future existence, billions of years of experience, billions of lives, culture and science and philosophy and art and forms of flourishing we cannot currently imagine. All of that is on the other side of the filter, and the filter is here, now, in the 21st century, in the specific set of technologies and social challenges and political decisions that define this moment. Parfit put it in terms that are worth sitting with. We live during the hinge of history. The choice is made by the people alive right now, not in some abstract future generation, not by some more advanced and wiser version of humanity, but by people driving to work and watching television and arguing about politics and making dinner. Those choices will determine whether the hinge opens or closes, whether the story continues or doesn't. Consider the perspective from the far future, if there is a far future. Imagine a historian, thousands of years from now, writing about the 21st century. If civilization made it through, if the filter is behind us and the long future stretches ahead, that historian will look back at this period as the most dangerous passage in human history, the hinge that Parfit described, the moment when every risk came to a head simultaneously and the outcome hung in genuine uncertainty. They will examine the decisions made in the 2020s, the 2030s, the 2040s with the same close attention that we now examine the decisions made around the Cuban Missile Crisis, or around the Treaty of Versailles, or around the printing press. They will understand that the people who lived through it were largely unaware of the significance of what they were doing, that the people making the decisions about AI governance didn't know they were writing the policies that would determine whether AI became civilization's salvation or its end, that the people debating climate policy didn't know they were deciding whether complex civilization would persist through the next century, that the people managing nuclear arsenals didn't know they were carrying in their hands the decision about whether humanity would have descendants. And if that historian exists, if there are descendants to write that history, it will be because people in this period did enough of the right things, made enough of the right choices, built enough of the right institutions, that the filter was cleared. Not perfectly, not without loss and damage and the accumulated weight of all the mistakes that civilizations inevitably make, but well enough, narrowly enough, that the story continued. That future is not guaranteed, but it is not foreclosed. The silence of the universe is a warning, not a sentence. The great filter is a description of what has happened, not a prophecy of what must happen. And the difference between a graveyard and a nursery, between a cosmos full of the ruins of civilizations and a cosmos on the threshold of its first great age of intelligence, That difference might come down to us, to what we build, what we prioritize, what we refuse to do, what we choose to value. Enrico Fermi died in 1954, 4 years after his famous lunch conversation, having spent his last years at the Institute for Nuclear Studies at the University of Chicago. He lived long enough to see the hydrogen bomb developed and tested, an order of magnitude more powerful than the atomic bombs he had indirectly helped create through the Manhattan Project, capable of destroying not just a city but a region, capable in large enough numbers of triggering the atmospheric changes that could end civilization. Whether he thought explicitly about the connection between his lunch question, "Where is everybody?" and the new weapon humanity had built, we don't know. He didn't leave a record of that thought. But the connection is there, unavoidable and stark. The civilization asking where all the others went is the same civilization that has built the tools most likely to make itself the next absence in the cosmic silence. There is something almost unbearably ironic about that. The species capable of wondering whether it is alone in the universe has built the instruments that could ensure it remains alone. And the species with the intellectual capacity to derive the Great Filter hypothesis is the same species that might be approaching the Great Filter right now, without the collective wisdom or coordination to navigate through it safely. Frank Drake, who died in 2022 at the age of 92, spent his entire career on the hopeful side of this question. He designed the first systematic search for radio signals from other civilizations. He convened the Green Bank Conference and gave us the equation that bears his name. He stayed active in the SETI community for 6 decades, maintaining the belief that the universe was not empty, that the silence was merely the result of insufficient technology and insufficient time, and that eventually the search would find what it was looking for. He was known as the father of SETI, and he died still believing. Whether his hope was well-founded, we don't yet know. The search continues without him, with better tools and larger datasets and more computing power than he could have imagined when he first pointed an 85-foot radio dish at 2 nearby stars in 1960 and listened. And whether it finds anything in the next decade or century, whether the universe turns out to be full of voices or empty of them, the search itself is part of the answer. It is the answer that says, we are not resigned to the silence. We will not simply accept it. We will keep asking, keep listening, keep building better instruments, keep refining the question. That determination, that refusal to let the silence be the end of the conversation, might itself be the thing that distinguishes a civilization that makes it through the filter from one that doesn't. Not the determination in a naive, cheery, motivational poster sense, but the determination grounded in clear-eyed understanding of the stakes, the risks, the weight of what the evidence suggests. The determination that looks at the graveyard and says, not us. Not yet. We know what the filter is. We know what it has done to others, and we choose differently. The Fermi Paradox is ultimately not a question about aliens. It is a question about us. It is a question about what intelligence does with itself, where it tends to go, and whether it has a future. The aliens, if they existed, if they rose and fell on worlds we have never seen, are part of the story, but they are not the main characters. We are. We are the civilization that found the paradox, named it, built frameworks for understanding it, and now has to live inside the answer. The universe may be a graveyard. Its silence may be the echo of 1,000 civilizations that couldn't make it. But we are still here, still asking, still reaching. And that aliveness, that refusal to simply become another silence, might be the most important thing about us. Not our technology or our art or our capacity for abstract thought, as extraordinary as all of those things are. The most important thing might be this. We are the civilization that learned to look at the cosmic graveyard and ask what it takes to not become part of it. We don't know yet whether we will succeed. The filter might be ahead, and we might fail. The universe might add our silence to the collection, but it might not. And the difference between those two futures, the graveyard and the garden, the last voice and the first chorus, might be the choices made by people alive right now, in this extraordinary, dangerous, hopeful, critical moment in the long story of matter, learning to think about itself. The stars are watching. Or maybe they're not. Maybe we're the only ones looking. Maybe we're the only ones who will ever know that they're beautiful. That is either the saddest thing in the universe or the most magnificent, or both. Go back outside tonight if you can, on a night clear enough to see them. Look up at the stars for real. Not through a phone, not through a screen, just the sky and your eyes. Find a dark spot if you can, away from the city lights, and hold still long enough that your pupils fully open. Let them fill with the light of stars that are so far away the light left them before humans existed. And while you're standing there, in that old, enormous quiet, think about what you now know. That those stars should, by every calculation we can make, be orbited by planets full of civilizations. That the silence you are standing inside is one of the deepest puzzles in all of science. That one answer to that puzzle is that something happens to civilizations, something they encounter on the road from where they started to where they hope to go, that ends their story before it can spread to the stars. That we are, right now, in the part of the road where that something might happen, and that we are, right now, alive enough and awake enough and informed enough to try to make it through. The universe may be a graveyard, but we are not dead yet. We are standing outside under the stars, looking up, asking why. And the asking, the refusing to simply accept the silence as an answer, is its own kind of declaration. It says, we are here, we are still here, and we intend to remain so. That's the story. That's why it matters. That's why the cosmic silence, for all its weight, is not the end of the conversation. It is the beginning of the most important one we have ever had.